CNNs, or convolutional neural networks, are one of the most powerful models for giving computers the gift of vision. They're used in self-driving, image captioning networks, and even GANs, or generative adversarial networks. The central idea is to have the model learn which features and patterns in an image are the most important. Here is my promise to you. I will provide the most clear explanation of CNNs you've ever seen in return for 5 minutes of your time. Let's get started. First, let's understand the input. We pass images into CNNs, which are typically represented as arrays of pixel values. For a 4x4 image, we would have a 4x4 array of numbers. The main calculation inside a CNN is called a convolution, and each filter performs a convolution. Each filter is just another array of numbers that slides over the input image, left to right and top to bottom, performing multiplications and additions. Now is a good time to clarify what a convolution really is. Given a 4x4 image, let's slide this 2x2 filter over the image and see what the output is. We overlay the filter on every 2x2 subgrid within the image, multiply the corresponding numbers and add them up. This is the calculation for the top left subgrid. Slide 1 unit right. This process repeats for the entire image. Also, CNNs have many filters, so if we had 10 filters, we would have 10 outputs. Since each output is 3x3, at this stage we have a 3x3x10 array of numbers. But let's say the ultimate task of this model is to classify the input image as a dog, cat, or bird. We would want to output a vector of size 3, where each entry corresponds to the probability that the input image is a dog, cat, or bird. So given this 3x3x10 array, the model would use a series of reshape operations, nonlinear functions, matrix multiplications, and even more convolutions to arrive at the final output vector of size 3. But there's one crucial detail we still haven't discussed: training. When we initialize a CNN, the entries in all the filters are random numbers, so the initial model predictions will be inaccurate. Over the course of training, the entries of the filters are updated until we're satisfied with the model's predictions. Through training, each filter learns to detect a unique pattern in the image. For example, one filter might detect a dog's tail, meaning when we slide that filter over the image, the output would be non-zero, but if we slide that filter over an image with no dog tail, the output would be mostly 0. But how are the filter entries actually updated during training? That brings us to gradient descent, the first ML algorithm I think everyone should learn. I have a 3-minute video breaking down gradient descent, which should pop up in the top right. If you enjoyed the visuals in this video, you'll love the visuals in the gradient descent video. I can't recommend it enough. See you soon.